we oh, not this one, this one. Okay. And this. Okay. Should be fine. Yeah. Today we'll probably finish early because we are only going to go through a very brief final review. And I guess before we go to final review, any question? What do we talk about last time? Last time we talked about let's still prove all this out, right? Wait, where is it? This one doesn't look. Wait, why didn't I have the amplitude amplification? Anyway, this time we go through the probably this one. Yeah, this time we go through a few more quantity. I guess quantifiers for Grover's algorithm, like whether m is known or unknown, and whether error is constant or zero, and we go through this generalization of a Grover algorithm, which is amplitude amplification. I guess this can be quantum or classical. You can think of this kind of like classical. Excuse me. You can think of this kind of like amplifying some classic algorithm that can partial solve your search problem, then you amplify its success probability. So your classic algorithm has success probability p. Then you can use Grover search to amplify the success probability using only order 1 over square root t time. And sometimes you can also think this amplitude as a quantum amplitude, because as you see, we are basically increasing the overlap with this beta mark state, and this u that is whatever state your algorithm prepare. So you can also think of this as a pretty quantum process, where you have a quantum algorithm that produces some state that has overlap to whatever desired space you want, or desired state you have, and then you can kind of use Grover algorithm, this to reflection equal to a rotation to amplify it. But anyway, that's the amplitude amplification, and we will actually skip the last part of this because it's a bit annoying to go through. And anyway, the calculation are here, so you can check it if you want. And here we will just jump to final review today. And once again, final will be on also class time, so next Thursday. And next Monday we'll just skip. Yeah. And final should be the same rule as midterm, so close book, but you can take 1 page of note. Okay. And final review are pretty short. I should pull all the midterm review. I can pull all these here. Why didn't I? Sorry, let me quick search midterm. Midterm review. Okay. Also pull out midterm review. Okay. It's easier. Okay. So yeah, the scope of final will be everything covered in the course. So obviously, since the midterm is also covered, and yeah, let's look through this really quickly. So in midterm review, we say there sigma x, sigma y, sigma z. Obviously, you should be pretty familiar with them now. And they have a whole bunch of things, whole bunch of properties. And the eigenstates, well, we mostly care about x and z. because they are real easier to use, and the eigenstate of z is 0 and 1, and the eigenstate of x is plus and minus. And the computational basis are whatever basis that you count from 0 to n minus 1 or 1 to n, depend on how you want to do counting. And then there are gates. So the multi-qubit gate, the most common one is the C0 one. And also, and also there is a headema. So headema will basically change between x and z. So you put the headema on the eigenstate of z, you become eigenstate of x. On the eigenstate of x, become eigenstate of z, etc. And there are C0, which is a very classical gate, but you can think about how it works on quantumly. And we use this Dirac notation and the Kate and Bra, you should be very familiar. And let's see, the measurement. So once again, we have 3 forms of measurement, but this will be not so much emphasized on final. I guess on final, here a very big tip. So we will check on some fundamentals. So you will still check on the Dirac notation calculation. As you will see in this 2021 final that will get posted later today. Yeah. So we still have some of those questions to make sure you still remember how the Dirac notation work. And also we will have the circuit calculation. So something like this, which you also see in midterm. And do we have it in review here? Yeah. And anyway, so the way you do this kind of calculation is, once again, you want to decompose the starting state to computational basis state. Then you can just calculate how every gate work on computational basis, because they usually have like easy rules. So you just keep the superposition on computational basis, then you can do the calculation pretty easily. Okay, so yeah, so those are some basic questions that will be in your test. Yes, any question? And also some part we skip that may or may not be appear. I think that's still pretty important are those density matrix calculations. So yeah. In particular, you are probably not going to see purification once again, but some kind of those reduced density matrix are pretty useful. And some of the, I think something very useful is the partial measurement. So like when you have an entangled state and you measure one part of it, and what's the reduced density, what's the post-measurement state or reduced density matrix of the other part that doesn't get measured. That's an important thing that you should remember after the course. So, yeah. So let's have maybe a note here. Okay. So now I'm partially telling you what is going to be in final. So this is going to be in final. This is going to be a final, and like entangled partial measurement might or might not be in a final. Entangled partial measurement, okay? Because that's pretty cool thing about quantum mechanics. So I guess not too much to be asked here. Okay. So those are things that we cover in the first part of the course. If you have a question, you can ask after the class or study more. And then things more on the later part of the course. So although we already covered this before the midterm. So phase key back is a very useful technique that you should always remember. And So when we talk about those, we talk about this in like George algorithm, right? We start using this in George. Oh, it's hard, George. Okay. Actually, both of those we use in George. Anyway, phase kickback is the idea that you can write your function value in the phase of your output state. So the setup is like this. We have a function that we are going to query as an oracle. So this oracle setting, I guess implicitly, is something you need to understand, because a large part of the code is set up in this setting. And so we have this function that's binary, so it's 0, 1 bit, n bit input string to 0, 1 bit output. And we think quantum oracle of this function, well, it will compute this function. So you have input x, then you should compute f of x. But it being quantum unitary, you need to be reversible. So actually, we'll keep this register, input register x intact, and it has the output register, and the output register can start in whatever thing. And we're assuming it's in some computational state A, and okay, so it's actually O plus here. Yeah. And okay. And so this being reversible, then you cannot just write f of x in the second register, so you will do this mod2 addition onto A. So if A is 0, then you will just write f of x here. But if A is 1, then it's basically negative of f of x, because everything needs to stay reversible. And anyway, so we spent some time. So that's a review of what the quantum oracle look like. So if you write this, it looks really like a classical oracle, because if you put x and a all classical, and even say you put a is 0 here, then it's just a reversible way to write the classical function. You will see x and compute f of x. And the way to make it quantum is doing this phase estimation. So we were saying we put A in computational basis state, but what happens if we don't put A in computational basis state? So in particular, if you put A in this minus state, then you do the calculation, you find out that you have input register X here, then you do this OF, and this record register actually stay unchanged, it's still minus. But you will get a global phase of -1 to the, I forgot to say X. Global phase of -1 to the f of x here. Okay. So instead of writing f of x into whatever in this register, you get this phase of -1 to the f of x if you put a minus here. Okay. And we can do a lot of analysis interesting with this -1 to the f of x. And this is the basis of the George algorithm and the bursting was running algorithm. Okay, any question? Yeah. So one thing to emphasize, we like to put this -1 to f of x here, but you want to think about it carefully. As we say, it's a global phase. So it's kind of, you can stick this -1 to f of x here anyway, right? So you can think of this -1 of x is sticking with this minus state here, and but it's really global phase. So you can multiply it with anything. That's why we can kickback it up here. Yeah. So that's phase kickback. And another interesting property, or a very useful property, when we were talking about George algorithm, is this headma to the n operation. So it's also a very quantum operation. Yeah, it's very quantum. So it's like a quantum generalization of making a uniform distribution. So headma to n. One way we like to use this is we will always use like headma to n times z to the n, and it will become the equal superposition of every x, right? And okay, let's be lazy, so I didn't write a normalization, but this will be like x from 0 to -1 and all the x. So this is like a way to create a uniform superposition if you input O0. But if you don't put O0, then there are some phase, and sometimes you can also do this head-map to the n on some weird phase state and invert it back. Remember, head-map to the n square equal to 1. Sorry, identity. That's really 1. Identity gate. Identity to the that's not sorry. Identity gate. Yeah. And yeah. So anyway, it's a quite quantum gate that gives you all the weird phase. So if you put it on O0 state, then you will generate this equal superposition of every computational basis state. And we even call this later in the global search, etc. But if you put it on other computational state, say this x as some n-bit string, then it is still equal superposition of every computational basis state. But now you get this weird -1 to -1 phase. And some of the y will get this -1 and some of them don't. And the rule is it's -1 to the x dot y. So this is like a inner product between x and y, and so it's an inner product between those bit strings. So inner product is like if x equal to like 0, 0, 1, y equal to 1, 0, 1. Then you inner product, so you multiply those together and add together. So inner product x dot y will equal to 0 times 1 equals 0, plus 0 times 0 equal to 0, plus 1 times 1 equal to 1. So that's 1, something like this. Okay. And yeah, so this formula is pretty useful. Okay. And those two concepts, although we didn't quite say, but they are kind of generalized to the idea of quantum Fourier transform and phase estimation when we are doing Grover's algorithm. Okay. So we have some gap between, so those are taught before midterm and those are taught after midterm, but it's actually there are some continuation. So you can see the head-map to the n are kind of generalized to quantum Fourier transform. So let's not go into too much detail, but notice that if you are not to the n, you just have h, then that actually equal to Fourier transform on two element. Okay. And yeah, but head-map to the n okay, so now I'm confusing you a little, but hopefully you can sort this out when you think this more carefully in class at home. So we are comparing head-map to the n and fn, and so this is okay. Let's compare the dimension of those two things. So head-map to the n is 2 to the n times 2 to the n dimension matrix, right? And there's Fourier transform, although we haven't said, but anyway, this is an n by n matrix. So you're kind of curious is head-map to the n, and we have head-map to the 1 equal to f2, and we'll kind of think will head-map to the n equal to f2 to the n, and the answer is no. Okay, and yeah, it's something different. Although you can also think it as a Fourier transform, but it's a different group than just the cyclic group of n. Anyway, so it's a little confusing here, but the quantum Fourier transform nevertheless looks kind of like this head-map to the n, and it's defined this way. And so it's also on computational basis, but now we don't write for now we don't quite think this as B string. So we think this is just as we say, Fn is a big N times big M dimensional matrix. And so J here is some big N dimensional Hilbert space. So we just count the computational basis from 0 to n minus 1. Okay? So J is some number from 0 to n minus 1. And we have this quantum Fourier transform unitary matrix that when you key it on a computational basis state J, then it becomes an equal superposition of all computer. Yeah. And okay. Oh, we forgot the very useful relationship here. And anyway, that's quantum Fourier transform. And then there is a HR1 over square root n here. And let's see. There's a very useful. Okay, so we should write it here. There is also a very useful relationship of the quantum Fourier transform, being those Fourier coefficient. We can think then they are the equal partition point on the complex plane, right? Those e to the 2 pi I. Oh, sorry, I'm missing over n here. So we have equal to 2 pi I is 1, then e to the 2 pi I over n is like nth root of 1 in a complex plane. And if add together all those n, add together n of them, then because they are equal apart, you can kind of convince yourself by symmetry that it should add equal to 0. And if you write out that in equation, it should be that some, let's see, so some k e to the 2 pi I j k. Now k is getting some over, so k from 0 to n minus 1, and this over n, then it is equal to 2 things. So it is equal to, so if j equal to 0, then this is always 1, then you are just adding 1 up 1 n times. So equal to n if j equal to 0, so that's easy. And if j not equal to 0, then as we say, you are adding up equal partition part on this circle of radius 1 on convex plane. And anyway, if j not equal to 0, then you can convince yourself by symmetry this addition up should equal to 0. Okay. And this is this is the identity we keep using when we do calculation around quantum Fourier transform. Okay. Okay. Any question? No. Okay. And the application of quantum Fourier transform is phase estimation. And since we are doing a quick review, let's not go into detail of how phase estimation works. But here is the here is the circuit of phase estimation. And you start with this 0 to a t, and you do Hedema to a t, and then you create equal superposition of every possible computational basis here. And so it's a bit confusing because this Hedema to a t here is doing the same thing as doing quantum Fourier transform here. Okay, because 0 is quite special as phase will stay all 0 here. But anyway, you do Hedema to a t here, and then at this point you will have like some k or possible k here, and we are skipping all the normalization. And then you will have u here, which is an eigenstate of the unitary you want to test. Okay, so we are in a setting that we have a unitary u that you want to test its phase, and we'll give an eigenstate u, and so it's eigenstate, so we'll promise that is equal to some eigenvalue e to the 2 pi I phi u. And we can write the eigenvalue as e to the 2 pi I phi because it's a unitary, so eigenvalue are always is non-1. And okay, and so what's interesting here is really like phase kickback. So yeah, so you can see this is like phase kickback because when you apply this control u to the k here, then each time you apply this u here, then you get some phase e to the 2 pi I phi here. Phase is like a global thing, so you can kick back the phase on the upper part. Okay, so actually the later part always stay u because you can just collect all the phase on the upper part, and so the upper part becomes this summation k and e to the 2 pi I phi k. So remember this e to the 2 pi I phi is this phase e to the 2 pi I phi here, and yeah, and you can see this phase is global, so you can kind of just write the parentheses here and see the upper part of some state that get this phase accumulated by doing this control operation, and you can kind of ignore the later part, the lower part as just the eigenstate u. And then you do QFT -1, and you see this has a really similar form to this QFT state, and you can get phi here. Okay, so that's phase A summation, and you can see that the QFT and the phase A summation really generalization of the phase kickback and the head to the n thing that we do in the easier algorithms. Okay, any question? Okay, and space kickback, and then there's Schwarz algorithm. And we don't go into detail of Schwarz algorithm, but I will just say there is going to be a question on this thing. Okay, and so the question will always look at this form. Okay, so we'll go through the kind of classical part of the global algorithm, and I guess the very high level thing to remember is Schwarz algorithm you first do is this period finding. Okay? So you will pick some number x, that's just whatever number, basically just whatever number co-prime n, and they will want to find its period r. Okay? And r being the so this r period is the smallest number such that x are equal to the 1 model. Okay? And yeah, and there are things that you walk through that's classical computation after you find r. And also remember there are some number series, group series around this co-prime thing. So let's say if you are n equal to pq, hopefully you still remember this thing. Kind of ISA thing, if n equal to pq, the number of integer, I guess. Yeah, okay, the number of integer that's between 1 and that doesn't matter, let's say 0 and -1. Okay. The number of integer between 0 and -1, that's co-prime to n. To n is, so those are actually a group. It's like a multiplication group, and the number of this group is p -1 times n -1. We spent quite a bit of time arguing this, although it's not directly related to Schwarz algorithm, but it's an interesting thing that nice to remember. Okay, and yeah, then you will be asked to walk through this basically phase A summation through algorithm that's used to do period finding. And remember, when we do period finding, so after you, okay, so if you can find this R, then you can do some easy classical calculation to find the vector PQ to do the short factoring. And the quantum part is the period finding or finding this R. And we do this by doing a phase estimation on actually pretty classical operation of this UX. So this X, same as this X. And UX, what they do is just multiplication. So you apply UX on any integer, so any computational state Y, then you get another computational state X times Y, and obviously everything should be modern. Okay? So this is just a multiplication, and we have a arguing class that the eigenvalues for this UX in the subspace generated from multiplying 1 with x. So if you apply ux on 1, then you will get 1x squared 2x to the r minus 1, and then xr to the r actually equal to 1, right? So this is like a r-dimensional subspace, or that I should say r-dimensional invariant space that's fixed by this ux. And so if you find eigenvalues in this subspace, there so this, or more like the face here, so this phi here, so the phi here will be, there are actually r different phi, and there will be s over r, where s is from 0, 1 to r minus 1. Okay. So when you do this phase estimation here on your UX, then you will find some random s over r. Okay. So that's the idea of period finding of Gover's in period finding part of Gover's algorithm. Sorry, not Gover's algorithm, Shor's algorithm. And yeah, you will have a question to work out some details. Okay. Question? If not, okay, we can probably finish before next class. And lastly, we have Gover's algorithm. Okay. And yeah, as a review, let's just talk about the most core part of Gover's algorithm. So it's that if you have 2 reflections, then it will equal to 1 rotation. And in terms of the Gover search algorithm, so I guess we should write a little more here. So we have OF. So for Gover search, we have, once again, this is the Oracle problem. So f is 0, 1 to the n. It's easier to say f is some integer from 1 to n to 0, 1. Okay, and then we have a quantum oracle of f, and we want to find x such that f of x equal to 1. This is the search version. Okay. And anyway, when you run Gover's algorithm, and okay, so such x is also called marked item. Okay, marked item. And when we run Gover's algorithm, then we'll start with this equal superposition of all x. So we will apply Hedman on 0, and we will get this equal superposition of all x, some x from 1 to n. Okay, and then we'll consider this 2-dimensional subspace of beta being all marked item, and alpha being all unmarked item. So beta are some x such that f of x equal to 1, and alpha are some x such that f of x equal to 0. And we see that when we do Gover iteration, we'll do 2 reflection. So the first reflection is, so reflection 1 is, well, let's say it's OF, okay? And in this two-dimensional space, actually not in two-dimensional, in any space, is, let's see if I remember this correctly, it's I minus 2 beta, right? Yeah. So it's it's a negative reflection around beta. So on this two-dimensional, I think it's a reflection around this alpha line. And reflection 2 is I think it's 255 minus identity. Okay, so it's a reflection through this phi. And anyway, so you have a reflection around this line and a reflection around this line, and it become a rotation of twice this angle, and so it's become a rotation of angle theta. Okay, and then we have the other picture. So so we still think about this space spanned by alpha and beta. Then our Grover algorithm will be keep doing rotation, so you keep do Grover iteration. So you have this OF and you have this, I think it's called G. Do we call it G? Okay, let's not write this because it might be different notation. But anyway, so each Grover iteration we do 2 reflection and that's 1 rotation of angle theta. So we keep rotating angle theta and we are hoping that we end some place around this alpha. Then we do computational basis measurement and we can get alpha. But if we are so if we do this iteration n time, then this angle here should be n plus 1 half theta. And if we are stopping at whatever time, then the success probability will be sine squared this angle. So sine squared n plus 1 half theta. And you can do some calculation here carefully, and you see that the theta is about the order of square root n over n, where m is the number of mark items. And so let's write this, m is number of mark items. Yes. And yeah. So that gives you that the query complexity of getting somewhere here should be order square root n over n, and we also have a lower bound showing that this is optimal. Okay, so theta n over n to find the mark item. Okay. And obviously there are caveats. So caveats are you need to know m, and you have some error probability. Okay, and we have lower bound interesting to know. And also we have application of Grover's algorithm. So for example, we run through collision problem, and another example. So those are actually pretty classical, but okay, but I guess, yeah. So you just need to find the part that you do search to apply the Grover's algorithm. So I would say kind of classical. Okay. But you need to search through unstructured thing. Okay. And we have seen that when we do collision, we do something more interesting, smarter, that we look through a whole set, then so we remember one set, then we search through another set and look through the pair, etc. Okay. So that's more involved. But for last year's test, we have easier problem. So what we are doing is, okay, so it's a whole bunch of notation here. But basically what I'm saying is we are doing triangle finding. So let's do, we have 10 minutes, okay? So yeah, so one of the easy way to get Grover speed up guess, is look at graph problem. So remember, computer science graph are composed of vertices. Sorry, vertices and edges. Okay, so a graph has like a vertex set, so those should be dots. Yeah, so vertices are just a whole bunch of dots, and so usually the vertices are just labeled like computational states or maybe 0 to 1 or something, and then there are edges that connect the vertices some way. Okay, so whatever. Let's draw a planar graph, although the graph might not always be planar. Okay, so graph look at this. Okay, and let's here keep things simple. Let's say edge only connect two vertices, and there is no direction or anything. Okay, so on the rectangle graph, it might have something like this, maybe. Yeah, so that's a graph, and a large set of quantum. So you can think about the query complexity on the graph. So you usually formulate this way. So you will query 2 points. Okay. So this is called adjacency matrix model. I think we talked about this in a very small slide. But anyway, the adjacency matrix model is your query. So remember when we talk about query, we say we query like some x. So x will actually be a pair of vertex here. Okay. So yeah, so now it's very simple. So you will say, well, input is maybe this vertex and this vertex, and then so f of x actually equal to f of v1, v2, right? Or equal to, and output is binary 0 to 1. So 0 is not connected, right? Not connect, and 1 is connected. So this is a adjacency matrix model. And yeah, so with this adjacency matrix model, then you can ask a whole bunch of questions on your graph. And so for example, we have a question of asking how do you find the triangle inside this graph? So a triangle means that if you have, so we have no triangle here, but if we want a triangle, so triangle means that there are 3 vertices that all of them are connected. Okay. Okay. So yeah. So this is actually still an open problem of what's the optimal query complexity of triangle finding if you use a quantum algorithm. Okay. So triangle finding. So classically, so we are talking about worst case. Classically, this is believe. So there is nothing too smart, nothing smart you can do. This is omega v squared. Okay. And yeah, this is the worst possible because so if we only talk about scaling in number of vertex, right? Number of vertex, then the number of edge, okay, so I should say theta, right? Although the upper bound is trivial. Okay. So number of vertex is v. Then the number of edge at most is v choose 2, and that's order v squared. Okay. So yeah, so classically you basically need to query every vertex, need to query every edge to check where is a triangle. But quantumly, so quantum, The lower bound, base known lower bound is omega v. Okay. I believe it is still tight. And the upper bound is something funny. And the upper bound, so it's very easy to get order v to a 1.5, which is the quadrant we have in our final. And but I think the base is like 1.3, like 2 something or 3 something. Yeah. Anyway, there is still a gap between lower bound and upper bound. And so that's a lot of digression, but the point is base no. Yeah, the point is how do we get this 1.5 upper bound? Anyone has a really quick solution? And anyway, okay. And so anyway, hint here is 1.5 is 3 divided by 2. Okay, so this is actually a very brute force algorithm. You just search through all triangles. Okay, so you just look through every triplet of points. Okay. Okay. So the number you need to search through is n to the cube. Okay. Oh, not n. I keep saying n. But okay, let's say n equal to is v. So easier. So n to the cube. No, actually, not do this. So let's say. Yeah. So number h to the cube. And so if you want to check whether 3 points are a triangle, then each check you only need to do 3 queries, right? You can query this edge, all 3 edges, and then to see if they are a triangle. Okay. So now you go over through this, search through all triplet, then the number query is order square root of this v cube and times, so each query for your go over needs 3 queries, so times 3, but 3 is a constant. That's order v to the 1.5. Okay. Yeah. So that's an example, and you might get another graph problem in your final. Okay. Okay. So any question? Otherwise, we will finish here today. Yeah, then we'll finish early today, and good luck on the final. Next Monday we'll skip. Yeah, yeah, and yeah, if you haven't done it, you can fill out the class evaluation. Yeah. Okay. Yeah, so we will skip some of the class.